Okay, so we have a few goals today when we look at differentials. Basically, we're going to be looking at, I guess the theme is kind of like how do we approximate things today with using a derivative. So the first goal is probably the most common one that we'll be seeing, and that is using a linearization. So that's a fancy word, meaning using a line to approximate a graph. So to give you an idea of how this works, I've got a couple scenarios here. So if we talk about scenario number one, we have a graph like y equals x squared, and here's the tangent line at the point 1, 1. Now what you can probably see is that it's not a very good idea to use this line to represent that parabola if I was out here, because there's quite a gap which would represent some error. But you'll notice that as I get closer, it's pretty close to that parabola. So in the second scenario, it's just zooming in to show you how much closer it looks like the function. That line hugs along pretty close for at least about that much of the picture. And if we keep looking as we keep zooming in, we've zoomed in even more. That's even better than, and here the pixels don't even, they blur together completely. I mean, you can see that the scale here is fairly small, but again, the point is that if we're using close enough values, the tangent line can approximate the graph. So, question, yeah?
Is this like epsilon delta?
No, nothing epsilon delta here. So, shame on you for saying those words. So a couple of things, just so that everyone, we're just going to talk about using a line, and that's the idea, but you should know that your calculators do similar things because, for example, if I was to ask you without your calculator, how do you calculate the sine of 0.3? It's very challenging. In fact, those difficult functions, we don't actually have a direct calculation. Your calculator has like a polynomial approximation. And because it only shows you 8 decimal places, as long as that polynomial is close enough in accuracy, you won't tell the difference, right? So approximation is actually used a lot in the real world just for practical purposes. Another reason you might do this, for example, let's say you had a polynomial with 100 terms. That means you'd have 100 multiplications plus 100 exponentiations when you calculated that. And then you'd also have 100 additions and subtractions as you added it all up, right? Because it could be like x to the 100 plus 5x to the 99, and so on and so on and so on. But you might say, why am I doing all 100 terms when I may only be interested in a very small area? So you may just want an approximation like this line that can do it real fast. One multiplication, one addition. So there are a lot of practical purposes, but for us, we're just going to look at how we could use a line. So there's a few formulas that you may, this is the one that you should know. It's the point-slope form of a line, and we're going to make use of that today. Now, the other two formulas that are shown up there are not necessary that you memorize them, but basically I'm just showing you how it goes from point-slope to a calculus derivative and point. So, for example, this is obviously the derivative at c, and this is the point c f of c. So it's basically substituting it in. Okay, and then all I've done in the last part here is I've moved this minus to the other side where it's become a plus. So I won't refer to those other two, but if you're the kind of person that likes to use formulas for your stuff, you may find them helpful. Yes?
Is this just like a formula to find the derivative at the point of the graph?
These second two formulas here, so if I call this 1 and 2, these are the formulas for the tangent line on a graph. Okay? This is the equation for a point-slope form of a line, right? So let's try it here with this example, and then we'll kind of get a feeling for how this works. So if we were to look at this, the line that's shown, this tangent line here, what do you think the slope of? Well, that's terrible. Let me try that again. What do you think the slope of that line would be? What would you guess? Yeah, you're almost right. The scale is a little different. If I go like this, that's 1 unit over. That's 2 units up. So the slope is actually 2, right? So the slope is 2. And the point that I'll be using at the tangent there, that's the point 1, 0. So I can approximate this curve. And I mean, looking at the picture, you might say, excuse me, you might say something like, well, I don't think I would go any further than there with it because then I'm starting to get very inaccurate. But let's see what we come up with here. This will be y minus 0 equals 2x minus 1. So I get a line of 2x minus 2. That's the equation of that line there. And notice I haven't actually given you the equation for that graph. But I can still use this line now to approximate the values of it. So for example, at 1.1, that's pretty close to the value 1. So I would expect it to be not too bad, probably fairly accurate. So if I wanted to estimate f of 1.1, I'm going to use the line. So I'll put in 1.1, and I get 2.2 minus 2. So I would estimate it to be about 0.2. And if I go even closer, if I go at 0.095, then I would expect this to be also not a bad guess or estimate. 0.95 minus 2. So this would be 1.9, take away 2, so it would be negative 0.1. So that would be my estimate for that curve at those two places. So, sorry, is that fair to people need a minute? All right, so let's take a look at this one here. Now, it's a good practice to try doing this. So I'm going to have you try finding the linearization at x equals 3. So again, when you hear that fancy word, linearization, that is basically making the curve into a line. And sometimes you might even hear the word local in there, because we don't want to think of this curve being good everywhere, like globally. We want to think of it being good only locally to use that line, right, very close to the point we used. So we're going to take a look here at x equals 3. The point is 3, 2. And I'm going to let you come up with the equation. Just try working through it to see that you're able to come up with this linearization as well for the square root of 1 plus x. And if you look at it, you might even say this time, oh, well, look, it doesn't even if I'm all the way up here, it's still pretty close, right? So it's a lot nicer to work with a line than it is to work with square roots. It's a lot easier to calculate as well. So anyways, try it your turn here. See if you can come up with a linearization at the point 3, 2. The first place we want to start is to know what that slope is. So to know what the slope is going to be, I need the derivative. And I'm looking for it at 3. So that'll be 1 over 2 times 1 plus 3. So this is going to end up being 1/4 for the slope. So point and slope, the line that hopefully you were able to come up with, would look like this. And if I rearrange this to look a bit more like how we would have it, and I'll combine this up, that means y would be equal to 1/4 x plus, so 2, that's like 8 out of 4, so we'd have 5 out of 4 here. Okay, so that would be the line that we could use to approximate it. Yes?
Is the line the same thing as off the one that's provided?
The line that's provided, you mean right here?
Yeah.
Yes. I didn't say that it wasn't there as an answer. I said it was a good idea to see that you're able to find that line. So the goal was that you'd be able to walk through the steps on your own and verify that you have the same line. So anyways, but yes, thank you for pointing out that I'm making you work extra. So let's take a look at how, how well suited is this idea of using a line. So let's try. What we're going to do is you're going to use the calculator to put in the square root of 1 plus x using our calculator. And then we're going to compare it to the line and see how much error we actually have. Okay, so I'll pause this while we work out the values. Okay, so I've set it up in my table. So I use y1, y2, and y3. And I got the TI-83 to do the table for me. So let's just take a look and compare about how practical this would be. So these are the answers I get for the actual values. And 2.0025. Now obviously they've been rounded here, so they're not complete answers, but that's the rounded form. If I was to look at the linear one, I get 2.05, 2.025, and 2.0025. And the error it's telling me here is negative 6 times 10 to the negative 4, negative 2 times 10 to the negative 4, and at this point here, negative 2 times 10 to the negative 6. So if you think about, when you do your calculations, most of us probably round to 2 decimal places, right? Or that's probably somewhere practical. There's more than 2 decimal places of accuracy for all those things we just tried. So again, it would be pretty practical as long as we only needed, 2 or 3 decimals of accuracy for an answer. So we're going to pause from this first idea of using a line to another idea of estimating how much change will result in a function. So here's the basic question that we want to know is if I was to move from this position to this one, right, and I call that delta x, how much will that affect the function? So here's the place that I first would have been. So this is f of a, and here's the place I'm now at. What I'd like to know is how much change in y will that be, right? How much does that affect the function itself? So if you take a look, this purple line in the graph is showing you the tangent line. So what we're going to do is, first we're going to go back to the Leibniz notation that looks like this. And you can actually think of this as a fraction. This is a very tiny, tiny change in y divided by the, a very, very tiny change in x divided by the corresponding change in y. So if this is where my tangent line is, here's the slope of the tangent line. You can see the tangent line, dx and delta x are identical, but this height here would be dy. So it approximates how much change actually happened. Here's how much we missed. Okay? And of course, as we shrink closer and closer, we get more accuracy as far as how much we're able to predict a change in the function. So to find the differential of y, this dy part, we're going to take the derivative and we'll use this notation. Whoops, I missed a few things in there. Notation. And then we solve for dy. So let me show you how this would work on an example, and then I'll have you try a couple by yourself. But again, when we're talking about this differential dy, we're talking about an estimate for how much the function will change. So I'll do the first one with you, which is y equals sine 2x. So that means the derivative here, dy dx, would be 2 cos x. So the differential would be 2 cos x times dx. And the scenario that we're using for all of these questions is x will be equal to 1, and the amount of change I'm introducing is 0.007. So dy my differential that approximates how much the function is going to change will be 2 cosine -1 times 0.007. So I'll get a calculator answer for you here, just so we can put a number to it. And it's about 0.0076. Okay, so what this means is, if you're at the point x equals -1, and you're going to move 0.007 in either direction, we would expect that's going to change the function by about 0.0076. Okay, so try it and see if you can come up with how much change will be introduced if we use these two functions but the same values for x and delta x. Okay, so for the first one, you'll get a derivative that's e to the x plus x e to the x. That means the differential is going to be e to the x plus x e to the x times dx. The place we're looking at it is at x equals -1, and the amount of change we're allowing is still, again, 0.007. And I believe if you plug it in your calculator, we would expect there to be no change here. Okay, and then in the next example, our derivative here is going to be 1/2 x squared plus 1 to the -1/2 times 2x. So if I substitute in the values, let's see here, the 1/2 and the 2 will work themselves out. So I would have, let's see, -1 over the square root of -1 squared plus 1. And it would all be times dx, which is 0.007. So -1 divided by 2. So I get about as much change as 0.00, let's call it 0.49. So now that we've had a chance to actually try calculating these, let's talk about why these might be interesting to estimate the change in y. How many people are going to study lab sciences next year, or in their future, if not next year? Something like physics or chemistry or biology, something like that. Okay, so here's the thing that you have to realize when you're doing those measurements, right, is, in your experiments, you're probably familiar with some of these error estimates that the tools you have provide. Like maybe your scale is plus or minus 1 gram, right? But the point is, let's say that I'm standing on a scale and it tells me that I weigh, I don't know, 170 pounds. Does that mean I guaranteed I'm exactly 170 pounds?
No.
Do you know how much I weigh exactly?
No.
If you don't know how much I weigh exactly, how can you figure out how much change? Like, if I eat a pound of food, do you know that that was a pound of food I ate? And if I stand on the scale, should it go up by a pound? Well, it gets very confusing because we have all this error everywhere. How do we keep track of it, and how do we, estimate it if we don't even know where we're starting has no error? So something like, I'll give you an example we're going to try here. To estimate how much we've introduced an error, we're trying to figure out how much that's changed our measurement, right? I stand on the scale, I get a measurement out. I'm trying to figure out how much will the error, the scale reads, tell me the change in my weight. So if we're taking a...
This is epsilon delta.
Not epsilon delta, no.
No, but it's like how much it changes according to how much it changes.
Oh, possibly, yeah, possibly. Okay, so here's the scenario we're going to look at, and just to give us an idea of how this, people in lab sciences will deal with this idea a lot when they go there. So a ball bearing is a 0.7 inch radius, and we've measured it with a caliper, and the caliper, we look on the box, it's 0.01 of an inch. That's how much accuracy the caliper has, okay? So you might look at all that and say, oh great, that's fine, I'm within 0.01 of an inch, but first of all, we don't even know really how accurate is that? Is that accurate enough for our purposes? How much error could that have introduced? Let's look at this example and say we use this ball bearing and we want to calculate its volume. Okay? So what we're trying to figure out is this error that's been introduced, how much does that affect the volume? We would be able to do this if we knew exactly what the volume is, but we don't, right? There's errors in it, so we're going to approximate it with dV. So the derivative of volume with respect to the radius is 4 pi r squared. Okay. That means that I can approximate the change in volume with 4 pi r squared times dr. In our example, we're using 4 pi, the radius is 0.7, and it's accurate to within 0.01 of an inch. So now what I'm able to do is approximate how much will this error affect the volume. So 4 pi, sorry. Well, at least it was a cool ringtone. So it looks like I have 0.08796 cubic inches. Oh, sorry, yeah, I forgot a squared in there. Thank you. So that would be slight change there. 0.06, let's go 16, okay? So that's about how much error we should expect, and if it's in inches, this is cubic inches that we've introduced. That's an estimate I can tell you. I estimate that I've introduced that much error into my measurement of volume. At this point, you might say, oh, it's not accurate enough for me to continue. I need a different tool. I need a better tool. You might also be curious, well, what percentage of this is it in the experiment? Like, that's only 0.0616. Like, who cares? It's so small. But we can try to find out the percentage error by saying, let's compare the error to its actual volume. So that would be, the volume is going to be 4/3 pi r cubed. Is it completely off now? Like, not just... Okay, famous last words. So 4/3 pi r cubed, and we're dealing with a radius of 0.7. So theoretically, if everything was perfect, we would expect this volume, 4/3 pi times 0.7 cubed, we would expect this volume to be 1.4368. So if I wanted to estimate how much would this affect my measurements, it's going to be 0.616. Sorry, that was too many. 0.0616 out of the volume I have. So in this experiment, I've actually introduced, and again, it's not 40%, there's an extra zero there, 429. I've actually introduced about 4.3% of an error. So it doesn't sound like much, but to put it in perspective, 4.3% error. Depending on what you're doing, that may be outrageous, that may be acceptable. So it gives us a way of doing these calculations without having to worry about, how do we find it if we don't know that we actually have the true measure. So differentials is probably the most one of the most common error propagation is probably one of the most common applications for a differential that you will see again sometime when you're doing lab sciences. But as far as our course goes, it's probably not the most common application that we would be seeing for it. This next one that we're going to look at, it uses the same idea, but this is more so like what you might be facing in an AP exam. something like this, which says, what if I gave you 16.5 square root and you had no calculator? How could you approximate that? 4.1? 4.1? Because it's close to 4? Okay, we can do better though. We can do better. And let's think about it this way. What would be really convenient to get rid of? It's 16.5. What would be really convenient to pull out of there? 0.5. So this is the idea that we're going to think about, is how can we treat this like 16 plus 0.5? So I'm going to walk you through how we can do this with a differential and no calculator to get a pretty decent accuracy. So here's what we've already talked about. We've said that that's delta y. So if I was to rearrange this, delta y plus f of x, that's what I would have here. And I would like to use delta x equal to 0.5 because I know how to do the square root of 16. But we can't rely on that because we don't have delta y. But what we could do is we could say that's approximately the differential plus the function. And let me show you how we can get the estimate then for 16.5 square root. Okay. So if I'm going to be finding a differential, I of course need a derivative. So if f of x is the square root, it's the square root I'm taking, then I'm going to want its derivative. So 1 over 2 root x. That means it's differential, and I guess it would be more appropriate to call this dy by dx. That means the differential is 1 over 2 root x times dx. Okay, so let's fill in. I could say that the square root of 16.5, that's approximately equal to, we're saying x is 16 and delta x is 0.5. So it's going to be approximately equal to dy 1 over 2 root x times dx plus the square root of x. So again, my approximation is going to be 1 over 2 root 16 times delta x, which is 0.5, plus the square root of 16. Now, let's see if we can do this here. This will be an 8th, so that'll be a 16th plus 4. So a quarter is 2.5, an 1/8 is 1.25, so 16 would be 0.625. So 4.0625 would be my no calculator approximation. Okay. And if I was to double check it, let's see what the actual value is. So 16.5 square root is 4.06202. Okay, it keeps going, but I round it there. So we actually have accuracy to the 1,000th decimal place with those differentials. Okay. So anyways, the theme again for today is approximations. If you know you can't get a guaranteed answer from it, chances are you're going to be using this section to make an approximation. Okay, and we will review some of the more AP specific and barren stuff as it comes up a little later.